Good morning, respective judge, committee, attendee of ICPM Malang 2020. Please allow me to introduce myself. I am Bonifacius Jovianto from University of Indonesia. In this opportunity, I would like to present my research evaluating the effect of structure-based configuration on reinforced concrete moment frame building performance with performance-based seismic design approach. This presentation content as shown, research method, research and discussion, and conclusion. Along with science and technological advancements, we are now be able to do complex design with ease. Paradigms of earthquake-resistant design have shifted, not only aiming for human safety, but also prevent economic loss. What we know in the past is the prescriptive approach, force-based seismic design, which is using response modification factor R, consists of overstrain, redundancy, and adaptability. While the new one, the latest one is the PBSD with nonlinear time history analysis. So three models are researched with variation on the structures based on X direction, named M1A, 1B, and 1C, 1A, 1B, and 1C. So in this research, nonlinear dynamic procedure is used with nonlinear time history analysis. So 11 ground motion are scaled to the target MCR response spectrum. The performance target for risk category 2 building under MCR is CP performance level. As can be seen here, the mean of 11 scaled ground motions are above 1.1 of the target response spectrum, while the mean of each pair of the ground motions are all within plus minus 10% of the mean of all ground motions. So first response to be discussed in average here is the average story drift and displacement response. On the left is response on X directions. Well, as can be seen here, increased structure bay results in reduction on story drift and displacement. 1A is orange and 1C is yellow. While on the right is the drift and displacement response for the Y direction. As can be seen here, increased bay configuration results in increased drift and also displacements. So in general, all the story drift and displacements are all below the 4% drift limit, but also can be seen here, it is far exceed the expected drift by the prescriptive code AC 716. So all these story drifts data are used, summarized and to recalculate CD, which is drift amplification factor by the prescriptive code. As can be seen here, CD values greatly varies between story. While it is not also universal for all the story as summarized by the prescriptive code. As summarized here, the CD value from the NDP analysis actually far exceeds the CD value from the prescriptive code, which is 5.5 for the reinforced concrete special moment frame. Next is the overstrain factor from base shear. As summarized here, is actually the average overstrain factor is still below the prescriptive code omega sub 0, which is 3 for reinforced concrete special moment frame. With increased structured bay has no effects on the omega sub 0, while the increased structure based on X direction is actually results in increased omega sub 0 on the Y direction. So next is the beam and column rotation DCR. Well, what is shown here is actually critical component maximum DCR on each story. With increased structure bay results in increased component DCR on both direction on X and Y direction. Based on the acceptance criteria, model 1A and 1B is categorized as IO performance because it is above between the EO and LS line, while the M1C is categorized as LS performance. So all those story drifts and base shear are used to recalculate our modification factor response R, which consists of overstrain, redundancy, and ductility. All these three factors are used multiply to gain the R final. So as can be seen, most of the buildings are unable to reach prescribed R value 8 for the reinforced concrete special moment frame. Well, this is the conclusion. That is all from me. Thank you very much. Thank you for your attention.